All right, so what type of symmetry does this f function have? Like, where could you fold it? It would fold on top of itself. Y-axis, yes. Did you say that? I just didn't hear you. Sorry. So this is y-axis symmetry. All right, and then if we're looking at the table or even on the graph, what do you notice about patterns in the ordered pairs? Like if you look at what -4 is paired with and what 4 is paired with. And same thing, -2 and 2. What do you notice? They're the same. So 4 and -4 have the same output. And same thing with 2 and -2. Now, if you said that in a different way, it doesn't mean it's wrong. You don't have to erase it. It's fine. This is just kind of for you to see what you can figure out on your own. All right, so let's say you were given the equation of a function similar to this, but you didn't have the graph, and you were trying to decide if it had y-axis symmetry. Can you think of a way you could do that? Just to check. All right, it's fine. What you can do is plug in opposites. And see if you get the same value. All right, so we have some notation that means that you plug in the opposites and you get the same value. And we'll write it on the other side, but what that means is that f of the opposite of x is equal to the same thing as f of x. All right, and then you might not know what this symmetry is for x cubed minus 4x. Have you ever seen that kind of symmetry? What does it look like it's happening? It's not just folded on a certain line. Anyone have an idea? Okay. Some people say it's like a rotation of 180 degrees. If you rotate it 180 degrees, it would rotate on top of itself. But what this is origin symmetry. I don't think you learned about origin symmetry until this class. Could be wrong. All right, and if we're looking at the ordered pairs, what patterns do you see? They're opposites. So 4 and -4 have opposite outputs. And same thing with 1 and -1. Right, so some notation we use to show that, this would be like g of -x is going to be the opposite of g of x. That's how you can write that using notation, algebraic notation. Right, so if you wanted to check to see if a function had origin symmetry, this time you could plug in opposites and see if you get opposites. And then the last question is to have you look at Anne Hathaway's face and see how symmetric her face is. It's kind of crazy. It's almost like she's an alien or something. But like pretty much all the parts of her face just line up across the y-axis. It's kind of crazy how perfect her face is. And a lot of celebrities will have extremely symmetric faces. All right, so let's look on the other side and fill in the notes. So that front side was just talking about symmetry, but this lesson is actually about even and odd functions. And even and odd functions are special functions that they're kind of rare. It's not that often that you have an even or an odd function. So an even function, or a function is even if it has y-axis symmetry. Okay, so I'm going to try my best to draw a symmetric graph where one side looks just like the other. Reflected though. Right, and then we kind of already figured out on the y-axis symmetry, if xy is on the graph, then negative xy should also be on the graph. So the y value for x and negative x is always going to match up on even functions. So f of negative x is equal to f of x. All right, and then I'll let y'all get caught up. And then a function is odd if it has origin symmetry. Okay, these are a little more difficult to draw. It's pretty close. A little wobbly. All right, so for origin symmetry, if we have the point xy on the graph, so origin symmetry kind of reflects it on the y and the x. And that's going to take it to the point negative x, negative y. So this time, f of negative x is going to be the opposite of f of x. So opposites will have opposite values. Now, sometimes something that you might be asked to do is to prove algebraically that a function is even or odd or neither. And it gets a little confusing. But what you're going to do is plug in negative x for x. And then simplify it down. So that really is just going to involve raising negative x to either an even power or an odd power and deciding if you would get an even or if you would get an odd. Do you guys know what happens with negatives? Let's say you raise negative x to an odd power, like the 7th. Do you know if that would give you a negative or a positive? Somebody knows. A negative. An odd number of negatives is going to be a negative. And an even number of negatives, we'll say to the 8th, is going to be a positive. So anytime it's an odd number of negatives, it gives you negative. And an even number of negatives gives you a positive. And so that's really all you need to know to figure this out. So we plug in that negative x, we raise it to the powers, just figuring out if we get negative or positive, and then you compare it to the original. If we plug in negative x and we get the exact same as the original, that means that it's an even function. So when we compare, if it's the same, then we're going to say even. if we compare and all signs change. It's the complete opposite as the original, then we're going to say odd. Right. And then the last thing that could happen is that some signs change and some don't. And when that happens, we're going to say neither. All right, so on number 1, we have half of an odd function. So we just have half. They're telling us it's an odd function. We're going to sketch the other half. So I'm going to start with this point right here. What is the ordered pair there? 7, -2. If this is an odd function, what ordered pair should also be on the function for odd? We're going to change them both. So it should be -7, +2. Okay, I'm going to do this one right here. It's probably not necessary, but I just want to practice as many of these as possible. So this is the point 5, -1. So if this is an odd function, what else should be on the graph? -5, +1, good. All right, and then this is the point 3, 0. So when we go to change the sign, 0 doesn't have a sign, and so we can only change 3, so that means -3, 0 should also be there. All right, and then we have a whole bunch of like fractional points, and then we get to the point 0, 3. So that means we should also have 0, -3. And then we're just going to connect those in a similar shape. So this is a line segment, so that's pretty easy. And then we have to do a quarter circle. Try your best. I did this really great last class when I wasn't recording, so I hope I'll do it good again. Well, that's not as good. That's okay. All right, any questions? And then it also looks like we've reflected it over the y and the x, or rotated it 180 degrees, but that's the other half of the odd. Do you know what it would look like if we did the other half of it even? It's a lot easier to do even. You just reflect it on the y, so it would be like this, and then like this. So I think you have to do both when we do our assignment, but anyway. All right, let's keep going. So on number 2, we know that the point 3, -18 is on the graph of an even function. What other point is guaranteed to be on the graph? -3. And for even, would it stay the same or would it be opposite? Even is going to stay the same. Why are you guys so tired? It's been a long week. All right, let's look at the next one. This one is the toughest one out of all of them. So we have this function, and we want to decide if it's even, odd, or neither, and we have to prove algebraically, which means we're going to do this thing right here. So if you were going to guess, would you guess even, odd, or neither? And it's okay if you're wrong. Anyone have a guess? Odd? Just say even or neither? Anyone think even? Anyone think neither? Okay, let's see. What we're going to do to prove it is we're going to plug -x in for x. So all of our x's are going to become negative x's. All right, and then we're going to do what I was talking about up here, we're going to raise those negative x either to an odd power and get a negative, or raise them to an even power and get positive. So this is odd, so it's going to be negative x to the fifth. This one's also odd, it's going to be negative x to the third. And then the plus 3 just drops down. There's no x to worry with there. Alright, so when we compare these, one of 3 things could happen. Either they're exactly the same, which they're not. That's what would happen if it was even. If it was odd, then every single sign changed. Did that happen? No. So then if some signs change, like these 2 changed, but this one didn't, then it's going to be neither. So it either has to be exactly the same or exactly opposite to be even or odd. All the other times is neither, which is a lot. Okay, and then on number 4, we're going to decide true or false. And if it's true, we're going to explain why it's true. And if it's false, we're going to give a counterexample. All right, so A says that all even functions go through the origin. Do you think that has to happen? If it's even, it has to go through 0, 0. No way. We have 2 examples of even functions on this note sheet that's not true. So we drew this one that's even. It does not go through the origin. The one on the other side is even. It does not go through the origin, so that's false. And a counterexample, we could draw either one of those. Even function, not through the origin. It's definitely not a requirement. Alright, and then B says that if each term in the polynomial function has an even exponent, the function is even. What do y'all think? That is true. And it's true because when you take those even exponents and you raise the negative to the even, it's always going to be positive. You'll always get what you got originally. So let's see if I can say that in less words. So this is true. And we're supposed to explain why. So raising negative x to an even power results in a positive. So f of negative x is going to end up equaling f of x. It'll be exactly the same.